So when we have a two-way table where we have our data organized for two categorical variables, that's our observed values. We can compute our expected values if there was no relationship between the two variables, and that would be your row total times your column total divided by your table total. And you do that for every cell in the table. And then we want to compare the observed values to the expected values to see how far apart they are. When they're really far apart, we have strong evidence against the null hypothesis. And so the distribution we're going to use is called the chi-square distribution. Our test statistic is called chi-square. That's a Greek letter. Looks kind of like an X. It's pronounced chi. If we spelled it out, it'd be CHI, where the CH is making the sound. Chi-squared. So what you do, here's the computation if you had to do it. You do your observed minus expected. In any particular cell, you've got your observed value. You've got the expected value if there was no relationship between the variables. And you find the difference between those. And then just like we do with standard deviation, we're going to square that, because if we added up a bunch of differences, some would be negative, some would be positive, and they would cancel out. We'd lose track of the error. So we square it, and then you divide by the expected value. So I look at that as the top is measuring how far apart they are, and then when you divide, you're doing it basically as a percent or as a proportion of the expected value. And so each cell, you do one of those, and then the capital sigma, that's our sign in math, to sum them up. So for every single cell, you do this observed minus expected squared divided by expected. You add those up for all the cells. That's the chi-square test statistic. And so it's a method that's approximately accurate and becomes more and more accurate for the distribution that we're using as the cells, as the size of the cells, the numbers in the cells get larger and larger. So a general rule of thumb for when it's safe to use chi-square: you want no zeros in the table. You want all the expected counts to be at least 1. And as it says here, no more than 20% of the expected counts less than 5. So you want most of them to be bigger than 5. You want no more than 20% of the counts less than 5, and none of them 0. And they point out in particular, if you have a 2 by 2 table, one cell is 25%, which would be too much. So they would all have to be greater than or equal to 5. So those are our conditions based on the size of the numbers in which it's safe to use chi-square, that it's accurate, assuming you have random samples. So here's a look at computing that chi-square test statistic. So you have your observed counts, and then for every single cell, all 10 cells here, I would do my row total times my column total divided by my table total, and I've done that for all 10 and got the numbers in the table here. And then for each one you would do this. I've done one example. Let's take that first number, the male science cell here, where male and science are intersecting. So we have 200 for the observed, 191.25 for the expected. We would find the difference between those, square it, and divide it by the expected value, 191.25. And that comes out to be 0.4003 if we round it off. And you would do that, in this case, 10 times. You would do it for each cell. Add them up, that's the chi-square test statistic. And so I've shown a few of them here with the ... meaning do it for all of them. Add it up, and in this case it turns out the chi-square test statistic is 24.067, which is pretty large. We're going to wind up getting a small p-value here, as we'll see in a minute. But before we get to the p-value and the test of significance here, so the chi-square test is an overall test. It'll tell us, period, whether or not there's a relationship. It doesn't tell us which cells in particular. So like in my example, if we get a significant result, we know there's some sort of difference between the majors that males and females are selecting, but that doesn't tell us which majors in particular are different. You'd have to do some sort of follow-up analysis. One way is just to look at the difference between the observed and the expected cells, which one have the highest values. A nice way to do that, and these are actually very closely related, because a nice way to do that would be to look at the chi-square test statistic values for each cell. The larger those are, the larger the difference is between the observed and the expected count. So if you can make a matrix or a table and look at the values for each individual cell, the larger ones, that's where the bigger differences are. And so your chi-square test, it always basically has the same hypothesis if you just insert your particular categorical variables. Your null hypothesis is that there's no relationship between the two categorical variables. The alternative is that there is. Okay? You may be able to put a better real-world interpretation on that depending on what they are. Like for instance, in my example that I'm doing in this section, we have males and females, which we could call the sex variable, and then we have their intended major. So the generic interpretation, the null hypothesis, is that there's no relationship between an individual's sex and the college major they're going to choose. maybe a better way to say that is that there's no difference in the majors selected between males and females. The males and females select similar majors at the same proportions. The alternative is that exactly the opposite is true. There is a relationship between the two variables, meaning in the case of my example, there's a difference between males and females, depending on which gender is going to affect the types of majors that they select. They point out, you could think it's always, in this case that we're doing, it's two categorical variables, but one of those categorical variables could actually be different groups in an experiment or something. So you can use, when you have independent simple random samples from two or more populations, so the different populations is one of your categorical variable, and then you have some other categorical variable you're looking at. Chi-square could work in that case. It could also work when you have a single population and two different categorical variables. The test statistic, where all of these hypothesis tests we look at, they come down to there's some sort of distribution. You have a density curve, in this case the chi-square distribution. The area under that thing is 1, and we find the certain proportions corresponding to the area that we need, which will give us our p-values, our probabilities of getting values as extreme as the chi-square we get from our data. The graphs, you can see some pictures of them here. They're skewed in this case. When you have degrees of freedom equal 1, it actually goes off toward infinity, but after that you get a hump where you have a peak and then it's skewed to the right. And as it gets bigger and bigger, it starts approaching again sort of a standard normal looking image, but anyway, the chi-squares in general, they're skewed to the right, have the peak there on the left. If you're using tables, or even when you report, if you're not using tables, we have to report degrees of freedom because that's the way we do it. The degrees of freedom, there's two numbers that are involved. You have a 2 by 2 table which has a certain number of rows, certain number of columns, and the degrees of freedom is r minus 1 times c minus 1. Number of rows minus 1 times the number of columns minus 1. Remember when we do the one sample t-test, it's n minus 1, sample size minus 1, so it's kind of like that, but we have two dimensions. You have the number of rows and the number of columns, so it's r minus 1 times c minus 1. And so for our example that we were looking at, when we have our table here, our null hypothesis would be that there's no relationship between our two variables, gender and intended major, or sex and intended major if you prefer that description. And you could also interpret that as there's no difference between the intended majors for the two groups there, male and female, the two different populations. The alternative, there is a relationship, there is a difference in the intended majors for males and females. So we computed previously the chi-square test statistic was about 24.067. The degrees of freedom, if you were going to look this up in a table, or if you just wanted to report the degrees of freedom, this is a 5 by 2 table, so it would be 5 minus 1 times 2 minus 1, which would be 4 times 1, so the degrees of freedom is 4. Then to compute it, the Texas Instruments calculators has a cumulative density function. Just like the normal, it has a chi-square cumulative density function. The arguments are the lower bound, which on this test, this is always an upper-tailed test. You give it your chi-square value and you're looking for the probability you would get differences between the observed and the expected that large or larger. So we've got our chi-square value off to infinity, 1e99 is what we use on our calculator. And then, typo, well, let's check and see if I did this right. The degrees of freedom should be 4. I typed in 5, it should be 4. That may be the wrong p-value. I was going to do it on the calculator anyway. Let's check and see. Okay, so in the Texas Instruments TA 83 or 84, we go into the distributions, second, and variables, and you've got the chi-square. We want the cumulative density function, number 8. And I get the little menu. If you don't get the menu, you type it as I did there, but make sure we use 4 degrees of freedom. So the lower bound would be our chi-square value, which is 24.067. Round it off to 3 decimal places. Our upper bound, I'm going to do 1. Second, the comma to get the E99, so that's 1 times 10 to the 99th, or 1 and 99 zeros. Degrees of freedom should be 4. I'm going to paste that. And looks like it was just a typo. I wrote it correctly. You get the value. I must have typed it in the calculator correctly, but mistyped it on the slide there. 7.74. You look, this is in scientific notation. You got an E-5, so that's 7.74 if we round it off, times 10 to the -5th. which would be, if we shift the decimal point over, 0.40774. So an extremely small p-value. If this was a random sample from the population and there was no relationship between sex and the intended major, there's almost no chance we would have gotten this big of a difference between the observed values and the expected values. We have a very small p-value, so we have very, very significant evidence to reject the null hypothesis and make the claim that there is a relationship between gender and intended major.